it's a direction that needs more attention. Because if I take a look, people say, for instance, I don't like artificial intelligence or I'm against artificial intelligence. I'm not, but I see that in cosmology, we have a hard time to actually succeed with artificial intelligence. Demis Hassabis, he won the Nobel Prize for AlphaFold, for this protein folding. And when he gave his Nobel lecture, he had 3 criteria. What makes a successful AI application? Number 1 is know your feature space, and it should be really large. Like a human cannot understand it, so you really need a huge computing farm to resolve all of the parameters that you have in your problem. And the parameter space is huge, you cannot oversee everything. And the second criterion is know your goal function. What is my function that I want to optimize for? With AlphaFold, it was pretty obvious. You have the free energy that should be minimized, and then you know how the protein is folding. And the third part is you need lots of data in order to train your artificial intelligence. And if you now look at cosmology, what do we have? None of the 3. Do we know our feature space? No, because we don't have like 23 amino acids that we can combine to proteins. If we just assemble them long enough, we do not know what dark matter is. So what are we looking for? What's our feature space? Is it a particle? Is it a fluid? What is it?
Wait, what is a feature space? What's a feature space mean?
A feature space is the ingredients that you have. Like for instance, I would say if I have a galaxy cluster, I would say, okay, what do I need? I need galaxies. I need the positions of the galaxies. I need the velocity of the galaxies in order to describe such a gravitationally bound structure. But I also need the dark matter in this galaxy and the positions and the velocities. So if I want to understand how a galaxy cluster is taken together by artificial intelligence, I would need the position and the velocity of dark matter. If I do not know what it is, I cannot reserve part of this feature space for it. And then the second part is the goal function. What is the goal? I mean, do we really understand gravity to a degree that we say we can write down this optimization function? I mean, Demis Hassabis used the free energy for the proteins. What is energy in general relativity? Masses have to be defined, and the definition may not be unique. So there we struggle from the other side to say, from the GR point of view, from Einstein's general relativity, how can we write down such a goal function to describe, for instance, a galaxy cluster? Like I said, also statistical mechanics to describe it is not going to cut it. And then third, data. We can use simulations. We have lots of simulations, and in simulations we have, I would say, enough data to train, but this is very costly to store on the one hand, very costly to produce from the starting point. And the big question is it actually realistic? Are we training on something that makes sense? For instance, for strong gravitational lensing, there was an AI approach. And this AI approach trained on simulations because we do not have enough data from strong lensing from the observational point of view to train such a machine. So they used simulated data, and they found out that when they tried to recover the simulations, great rates, 100%, I mean, not 100%, but 95% recovery rate of the data and correct descriptions. But then they went to the observations, and then the rates went pretty much down because there was something missing in the simulations that was in the data. And so the training process was not realistic enough so that the machine could actually find all of the lensing events that were there, or that we actually know they were there. So there is something missing here. And last but not least, if you take the observations, like for instance, DESI has now found 11 billion, no, it was 11 million galaxies in our local universe, like 11 billion galaxies. Mm-hmm. That's not half of the population of Ghana. So just to put in a context, you have 11 million galaxies out to a certain redshift in a huge cosmological volume. And now compare this to what we know on Earth. I mean, population of Ghana, if I'm not mistaken, is 37 million people. So in a very small country in Africa. So if we now compare this to the 11 million galaxies in this cosmic volume, you know how the sampling is. I mean, we have a lot of data, we have a high degree of detail, but I don't think that it's enough to train an artificial intelligence. Leave aside the problems that we don't know what's actually in the observations due to dark matter, dark energy, and the unknown ingredients of the universe. And this is why I think we first need to understand ourselves. What are we talking about? What is dark matter? What is dark energy? And when we have these questions, I think we can use artificial intelligence. But so far, for the exploration process, we may get some hints where to go or not. But we cannot expect, for instance, an AI to understand the global mass distribution in a strong lensing event when I've already shown that only local information is the one we get from the data. So in that sense, the AI would just speculate better or give us a more sophisticated model, but we still don't know why this model, okay, it fits the data, but as do all other models, as I've shown.
Mm-hmm.
So what is the gain using artificial intelligence, for instance, in this problem if all we get back is a more complex model and even maybe a less transparent model that we cannot understand? I mean, if we get a more complex model and not just a power law, how do we now argue that this is reasonable physically? The machine may give us something that fits the data, but it's just one option of many. This is what we know. But then how do we argue that this is the true model? This is the truth that's actually out there. When we already know from the inverse problem, we cannot know this.
Now, I know you said you will be talking about this issue and your colleague may push back and you say, just give me a chance. Maybe I can't take the ball all the way to the end of the football field, but I could take it a few feet further. So allow me to ask, what changes if you get to the end of the football field? Like, paint that picture for me. What changes in cosmology? What changes in cancer research? Your method of prioritizing inverse problems over forward problems and your solutions via these inverse problems takes off. What does the future look like?
Well, I mean, inverse problem solving is, I would say, a typical thing that you use when you solve criminal cases. So now let's assume that we use it also more in biomedical, in astro and cosmology, wherever we have like complicated problems with maybe non-unique answers. So if we do this, I would say we have to rethink our scientific method completely. If we replace this forward modeling with this inverse problem-solving approach, it would mean that we change the way we think about science. And in my opinion, this would be a better world because we would have a more positive way of knowledge gaining. And I would like to show you how I mean this. I mean, imagine you now have this inverse problem solving method and you build a tree of necessary models from the trunk to the branches to the leaves. And every higher level is based on the assumptions on the lower levels. So in that sense, if you now think, I want to solve a problem and I have already built the trunk, and now from one branch, I want to go to a smaller twig. So to extend my model a little bit further. If I guess a little bit wrong, then I can only fall back to the level beneath this one, but I will not fall down the entire tree to the ground. This is what forward modeling sometimes does, that you end up at square zero and you do not know how to climb up again. And in this way here, we avoid this problem. And so I hope that this would be more positive and encourage more people to care about science, because if they have already built their trunk of knowledge of a certain part, then they only need to extend their knowledge a little bit. So that's more positive. And on the other hand, this is even more important, if we now take a look at how science is done, it's usually investing a lot of money into a high-risk, high-gain science research. If we now say we already have a solid trunk and we just need to extend it a little bit, it takes out the high risk of all of this. And another point that comes with it, if you now climb up the tree, the further you climb, the less choices you should get. It's like in a criminal case, the more evidence is presented, the more people you should be able to kick off your suspect list. So in the end, you narrow down the choices. And then this means you need fewer and fewer resources the higher you climb up. So this idea is highly efficient. it's resource saving. And in that sense, I think you could even fund more projects than before at a lower risk, of course. And so in general, I think if you build up all of this, it sounds more positive for me than gambling on certain forward models. And in the end, you may not even be able to find counter evidence or evidence in favor of something.
This is super interesting because theoretical physics is, in large part, model generation. So on the archive, almost every day is a new model. Here's how the universe works. Here's how even on this channel, theories of everything. New model. Well, here's how quantum theory works. Here's how it doesn't work. Here's how blah, 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 blah. Here's how GR works. Here's how you combine them. Here's what space-time is. Here's what space-time isn't. And then the question is, well, look, in absence of data, it's always caveated like that. In absence of new data, we don't have anything that's beyond the standard model. In absence of new data, what else are we to do as theoretical physicists? All we know how to do is just generate models, and we don't exactly have data to go by. So in your analogy, it sounds like what you're saying is that would be the equivalent of just adding more suspects to your criminal list.
Yes.
And that's the opposite of what should be done. You should be narrowing suspects down.
Yes.
But okay, I'm sure you've spoke to theoreticians about this, and this goes against the whole ethos. And again, like I mentioned, it's caveated with in absence of evidence. So what do you say to this throwing models to the wall and seeing what sticks? It seems like that's all that can be done.
Yeah, but on the other hand, I mean, there are people like Neil Turok who say we have a lot of data, so let's use it in a different way. Let's try to be minimalistic. And in that sense, to clean up, I mean, Bjarkén also said for particle physics that when they found all the new particles and they always inserted yet another field, yet another particle, and so on, so their model just grew. And he said that the discovery was so quick. They just added and it somehow worked out. But he said, we were always hoping that a few years in the future, somebody would come and clean up that mess. So they were obviously, they were putting together a model with a really hot needle because they had so many discoveries. But they thought in the end, hopefully somebody will look from top down in order to make sense out of this from a higher viewpoint and then to clean up the mess. And I think it's the same with all of these models that we have in cosmology or astrophysics. We're not short of models, but to compare them with each other, to find what do they have in common, where do they differ, why do they differ, all these things, they are the important things to do. It's not coming up with yet another model. It's trying to embed the model that we now have, that we want to put forward, into the landscape of all the other models. And in addition, also to relate them to the other models to say, here is where I differ, here is where I agree with the others. And this is what I did with my approach to say the maximum information is where all models agree. And then it's pretty obvious why and where the models will differ from each other and will differ from the information in the data.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.